Deflection of light. The bending of a ray of light thus described is much too light on the surface of the Earth to be observed. But the attraction of gravitation exercised by the Sun on its surface is, because of its great mass, more than 27 times stronger, and a ray of light that goes close by the superficies of the Sun must surely be noticeably bent. The rays of a star that are seen at a short distance from the edge of the Sun will, going along the Sun, deviate so much from the original direction that they strike the eye of an observer as if they came in a straight line from a point somewhat further removed than the real position of the star from the Sun. It is at that point that we think we see the star, so here is a seeming displacement from the Sun, which increases in the measure in which the star is observed closer to the Sun. The Einstein theory teaches that the displacement is in inverse proportion to the apparent distance of the star from the center of the Sun, and that for a star just on its edge it will amount to 1.75 seconds. This is approximately the 1,000th part of the apparent diameter of the Sun. Naturally, the phenomenon can only be observed when there is a total eclipse of the Sun. Then one can take photographs of neighboring stars, and through comparing the plate with a picture of the same part of the heavens taken at a time when the Sun was far removed from that point, the sought-for movement to one side may become apparent. Thus, to put the Einstein theory to the test was the principal aim of the English expeditions sent out to observe the eclipse of May 29th, one to Princess Island, off the coast of Guinea, and the other to Sobral, Brazil. The first named expedition's observers were Eddington and Cottingham, those of the second, Crommelin and Davidson. The conditions were especially favorable, for a very large number of bright stars were shown on the photographic plate, the observers at Sobral being particularly lucky in having good weather. The total eclipse lasted 5 minutes, during 4 of which it was perfectly clear, so that good photographs could be taken. In the report issued regarding the results, the following figures, which are the average of the measurements made from the 7 plates, are given for the displacement of 7 stars. 1.02 seconds, 0.92 seconds, 0.84 seconds, 0.58 seconds, 0.54 seconds, 0.36 seconds, 0.24 seconds. Whereas, according to the theory, the displacements should have amounted to 0.88 seconds, 0.80 seconds, 0.75 seconds, 0.40 seconds, 0.52 seconds, 0.33 seconds, 0.20 seconds. If we consider that, according to the theory, the displacements must be in inverse ratio to the distance from the center of the Sun, then we may deduce from each observed displacement how great the sideways movement for a star at the edge of the Sun should have been. As the most probable result, therefore, the number 1.98 second was found from all the observations together. As the last of the displacements given above, that is 0.24 seconds, is about 1/8 of this, we may say that the influence of the attraction of the Sun upon light made itself felt upon the ray at a distance 8 times removed from its center. The displacements calculated according to the theory are, just because of the way in which they are calculated, in inverse proportion to the distance to the center. Now that the observed deviations also accord with the same rule, it follows that they are surely proportionate with the calculated displacements. The proportion of the first and the last observed sideways movements is 4.0, and that of the two most extreme of the calculated numbers is 4.4. This result is of importance, because thereby the theory is excluded, or at least made extremely improbable, that the phenomenon of refraction is to be ascribed to a ring of vapor surrounding the Sun for a great distance. Indeed, such a refraction should cause a deviation in the observed direction, and, in order to produce the displacement of one of the stars under observation, itself a slight proximity of the vapor ring should be sufficient. But we have every reason to expect that if it were merely a question of a mass of gas around the Sun, the diminishing effect accompanying a removal from the Sun should manifest itself much faster than is really the case. We cannot speak with perfect certainty here, as all the factors that might be of influence upon the distribution of density in a Sun atmosphere are not well enough known. But we can surely demonstrate that in case one of the gases with which we are acquainted were held in equilibrium solely by the influence of attraction of the Sun, the phenomenon should become much less as soon as we got somewhat further from the edge of the Sun. If the displacement of the first star, which amounts to 1.02 seconds, were to be ascribed to such a mass of gas, then the displacement of the second must already be entirely inappreciable. So far as the absolute extent of the displacements is concerned, it was found somewhat too great, as has been shown by the figures given above. It also appears from the final result to be 1.98 for the edge of the Sun, that is 13% greater than the theoretical value of 1.75. It indeed seems that the discrepancies may be ascribed to faults in observations, which supposition is supported by the fact that the observations at Princess Island, which, it is true, did not turn out quite as well as those mentioned above, gave the result of 1.64, somewhat lower than Einstein's figure. The observations made with a second instrument at Sobral gave a result of 0.93, but the observers are of the opinion that because of the shifting of the mirror which reflected the rays, no value is to be attached to it.